The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, well, the result of which we obtained on Wednesday for spontaneous emission for the Einstein A coefficient, regarded as an accomplishment, as a highlight of the course. We've worked hard to talk about atoms and electromagnetic fields, and ultimately, to deal with spontaneous emission, it was not enough to put a semi-classical light-atom interaction, the dipole Hamiltonian, get Rabi oscillation and such, to put that into the picture. We really needed a quantized version of the electromagnetic field, and this is the result when an atom is excited and interacts with all the empty modes of the vacuum, and we summed up the probability that a photon is emitted in any of those modes. And by doing kind of all the averaging with the density of state for all the possible directions, we obtained the famous result for the Einstein A coefficient, which is also the natural line width of the atomic excited state. Do you have any questions about the derivation or what we did last week? Then I think I will just continue and interpret the result. So we got a result for an Einstein A coefficient, and well, the question is, how big is it? Well, it has a number of constants, and if let's discuss it now in atomic units. Well, if we assume the frequency or the energy is on the order of a Rydberg, that's sort of the measure for an electronic excitation in the atom. We assume the dipole matrix element is 1, that means 1 Bohr radius. Since we have pretty much said everything 1 and expressed everything in atomic units, it means that the speed of light is, remember, the velocity of the atom in n equals 1 was alpha times smaller than the speed of light. But the velocity of the atom is 1 atomic unit. So therefore, the speed of light in atomic units is 1 over alpha. And that means that if you look at the formula, there is the speed of light to the power 3 in the denominator. And that means that in atomic units, the Einstein A coefficient is alpha to the 3, which is 3 times 10 to the minus 7. So that means that the ratio of the spontaneous emission rate, which is also the inverse lifetime and therefore the natural line width of the excited state, relative to the transition frequency, so the damping of the harmonic oscillator or the two-level system relative to the energy spacing of the oscillator is small, it's actually alpha cube. So if we take this 3 times 10 to the minus 7 and multiply it with the atomic unit of frequency, which is 2 Rydbergs, we obtain on the order of 10 to the 9. And that's a rate of 10 to the 9 per second. And that means that the lifetime of a typical atomic level is on the order of 1 nanosecond. Well, often it's 10 to 100 nanoseconds because many transition frequencies are smaller by quite a factor than the atomic unit of the transition frequency. Remember, the Rydberg frequency would be deep in the UV, but a lot of atoms have transitions in the visible. I highlighted already when I derived it that the spontaneous emission has this famous omega cube dependence. And that is actually important to understand why lower lying levels, excited hyperfine levels, do not radiate. So let me just kind of formalize that. If I would now estimate what is the radiative lifetime for a transition which is not, as I just assumed, in the UV or in the visible, let me estimate what is the radiative lifetime to emit a microwave photon at a few gigahertz. Well, the microwave frequency, roughly gigahertz 10 to the 9, is 5 orders of magnitude smaller than the frequency 10 to the 14 of an optical transition. So therefore, this is 10 to the 15 times longer. And if we have typically 1 or 10 nanoseconds for an electronic transition, that means that the spontaneous lifetime for a microwave transition is several months. If in addition we factor in that hyperfine transitions have an operator which is the Bohr magneton, a magnetic dipole operator, not an electric dipole, and we discussed that the Bohr magneton is actually, when we discussed multipole transitions, we discussed that the Bohr magneton is alpha times smaller than a typical electric dipole moment. So therefore, a magnetic dipole transition is alpha times weaker than an electronic dipole transition. And that means now, if we multiply months, which we obtain by the frequency scaling, again by alpha square for the weakness of the magnetic dipole, we find that atomic hyperfine levels have a lifetime which is on the order of 1,000 years. And this is why it's very safe to neglect those transitions in the laboratory and assume that all hyperfine states in the ground state manifold are pretty much don't decay and are long-lived. Questions? Okay, so with that, we have discussed spontaneous emission. We have all, so let's go through a few clicker questions to discuss the subject and verify your understanding. So the first question is, can an E2 transition which is a quadrupole transition, can you drive it by a plane wave, or does it need a laser beam which has an intensity gradient, such as a focused laser beam? Yes or no? Okay. Well, the answer is yes. You can just use your laser beam. If a quadrupole transition would require a gradient, it would really require a gradient over the size of the atom, and that would be extremely hard to achieve. Fortunately, this is not the case, because what happens is we actually assumed in the derivation that we had a plane wave, e to the ikr, and then did a Taylor expansion. And it was this part of the Taylor expansion of a plane wave which gave rise to the matrix element for the quadrupole transition. So a plane wave, a laser beam is sufficient to drive higher multipole transitions. Next question. Can spontaneous emission be described as a stimulated emission process by the zero-point field? So by the zero-point field of, we know the electromagnetic wave is a harmonic oscillator, and harmonic oscillator is a ground state, and in the ground state you have zero-point motion, so there is an electric field even when we have the vacuum state. And the question is, can spontaneous emission be described as simply being stimulated emission, but now due to the zero-point fluctuations of the electromagnetic field? Okay, well, the answer is it depends. It depends if you just want to make a qualitative hand-waving argument. Then I would say you are correct. You can say that the electromagnetic field of the vacuum stimulates a transition. But when I said described, I meant if you can get it quantitatively correct. And there the answer is actually no, because the energy of the electromagnetic field is n plus 1/2 h bar omega, whereas the spontaneous emission rate is n plus 1. So you have half a photon worth of extra energy, but the spontaneous emission is sort of like, the spontaneous emission is the rate which would be stimulated by an extra energy of h bar omega. So in other words, you would get the answer wrong by a factor of 2. I think deeper in the quanto-electrodynamic description of spontaneous emission, you would identify 2 terms for spontaneous emission. One is actually the stimulation by the vacuum field, but there is another term called radiation reaction. So there are sort of 2 terms. Trust me, if not, there are hundreds of pages in Kohn Tanucci's books written about it. And in the ground state, the 2 terms destructively interfere. Therefore, you have no spontaneous emission in the ground state, which is reassuring. But then in the excited state, the 2 terms constructively interfere, and therefore you get spontaneous emission, which is twice as much as you would get if you just look at the stimulation by the vacuum field. So the answer is not quantitative, but half of it, yes, can be regarded as stimulated emission by the vacuum fluctuations of the electromagnetic field. Okay. We emphasized that spontaneous emission is proportional to omega cube. The question is now, what is the dependence in one dimension? If everything the atom can only emit in one dimension, everything is one-dimensional, put the atom into a waveguide. So your choices are omega cube, omega square, or omega. Well, if you press D, none of the above. But I can already tell you it's one of those three. So everything the same, but we are in one dimension. The world is now, the world seen by the atom and by the electromagnetic waves is one-dimensional. Yes, that's correct. As you remember, out of the omega cube dependence, omega square came from the density of states. And what is omega square in 3 dimensions becomes omega in 2 dimensions and constant density of state in 1 dimension. So therefore, in 1 dimension, we are only left with the omega dependence. And okay, so there is one factor of omega which does not come from the density of state. And the next question is, where does the other power of omega come from? And as we discussed, it's not the density of states. So we have 3 choices. One is it comes from the atomic matrix element. It comes from the dipole approximation, or it comes from the quantization of the electromagnetic field. Okay, the majority got it right. It's the field quantization. Sort of remember, when we write down the electric dipole Hamiltonian, in the quantized version, there is a prefactor, which is the electric field of a single photon. So if we have a single photon, it gives rise to an electric field squared, which is proportional to h bar omega, and this is sort of the normalization factor. Two more questions. We talked a lot about the rotating wave approximation, and we also talked about it that for a spin system driven by a magnetic field, if we have a rotating magnetic field, we do not need the rotating wave approximation, because if we drive a spin system with a rotating magnetic field, we have only the co-rotating term. The question I have now for you is whether the same is correct or not for an electronic transition. So therefore, the question is, for electronic transitions, do we always get the counter-rotating term? And if we want to have a simple Hamiltonian, then we do the rotating wave approximation. So the question is the rotating wave approximation necessary? And because we always get the counter-rotating term for the electronic transition, then the answer is yes. Or if we can, or are there examples where the system is exactly described by only one term, the co-rotating term. I will come back to that later in the class, but I thought it's a good question. Okay, let me give you the answer. I actually coincide with everybody in the class here, because I would tend to say no, because there are situations where the counter-rotating term can be 0 due to angular momentum selection rules. However, if you have an electronic transition and you have a sigma plus transition to one state, there's always a possibility for sigma minus transition. So you usually get both. But if you apply an infinitely strong magnetic field, then the m equals -1 state can be moved out of the picture. You have only, let's say, the m equals +1 state, and then selection rules mean that the counter-rotating term is vanishingly small. But it's an artificial situation. So you can all claim credit for your answer. Finally, the last question is about the lamp shift. We are now talking about electronic transitions, and the question is lamp shift. Is it due to the counter-rotating term? In other words, if you have a situation where the counter-rotating term is 0, as we just discussed in the previous example, that there may be situations somewhat artificial, but you could arrange for it, does that then imply that there is no lamp shift? So, yes or no, is the lamp shift caused by the counter-rotating term? Involved in electronic transitions? Okay. Okay. Well, what else is the lamp shift? It is the AC Stark effect of the counter-rotating term. So, sorry, is it due to the counter-rotating term? Yes, of course. The lamp shift is the AC Stark effect caused by the vacuum fluctuations. That's what it is. But we'll come to that because I want to discuss later today some aspects of the fully quantized Hamiltonian, and we will again in the fully quantized picture see the operators which are responsible for the co-rotating, for the counter-rotating term, and then I will point to the operator which causes a lamp shift. But before I continue, any questions about the questions? Colin?
When you derive the amplitude of the electric field due to a single photon,
Yep.
I always get the factor of 2 wrong. So you wrote h bar omega is 2 epsilon naught d e squared. Now there's a contribution that comes from the electric field and the magnetic field that gives you 1 factor of 2. Then there's always that other factor of 2. Are you getting that from using 1/2 h bar omega as the vacuum fluctuation?
I'm not going back to the formula because I run the risk that it was wrong. But all I want to say is, what I really mean is use Jackson, put in a volume V an electromagnetic field with h bar omega energy. And the electric field squared of this photon, that's what I mean. And if you find a factor of 2 mistake in my E square, I can still, get out of the rear exit by the rear entrance door by saying that there is also difference whether E square is E square RMS or whether E square is the amplitude. There are those factors of 2 everywhere. But what I mean is really the electric field caused by one photon. And of course, the argument stands, I don't need any factors of 2 or any subtleties of the electromagnetic field energy. We know that the energy is n plus 1/2, but emission is n plus 1. And this shows that the stimulation by the vacuum field cannot quantitatively account for spontaneous emission.
So the quantity that you set equal to is h bar omega, not 1/2. Not the sort of fluctuation, but the real...
Okay, if you want to know, let's not compare apples with oranges. You want an electric field, and you can pick whether it's the RMS field or whether it is the maximum amplitude. You can pick what you want. But now we are comparing what is the E square for the vacuum, for single mode vacuum, and what is the E square for single photon. The two answers differ by a factor of 2. A single photon is twice as strong in E square as the vacuum fluctuations in the same mode. That's what it means. Yes.
I have a question about the spontaneous emission rate. The explanation, the entire quantum mechanical derivation that we have. What did people not know what the formula, how to describe spontaneous emission rate mathematically before using quantiles?
I think so. I have not gone deeply back into the history, but a lot of credit is given to Einstein. And as I mentioned last week, that Einstein actually had spontaneous emission in his derivation for the Einstein A and B coefficient in this famous paper. And so he found that there must be spontaneous emission based on a thermodynamic argument. It's only spontaneous emission which brings the internal population of an atom into equilibrium. So I think it is correct to say...
Can you derive it from that Statman condition of getting equilibrium?
That's what Einstein did, and the answer is, by comparison with the Planck law, you get an expression for the Einstein A and B coefficient. Now, of course, you can go the other way around. You can say, if you just use classical physics, you would actually expect, now it depends, if you use the Bohr model, you would expect that the electron is radiating, and it was a mystery, how can you have an atom in the ground state which is circling around the nucleus and not radiating at all. On the other hand, in quantum mechanics, we are not assuming that the atom is circulating and we have an accelerated charge, and we have a time-dependent charge distribution. We use a steady-state wave function. So I'm not sure if there is maybe an argument which would say there should be some spontaneous emission based on a purely classic argument, but this would not be the whole story, because the classic argument would then deal with the difficulty, why is there difference between n equals 1, which does not radiate, and n equals 2, which radiates. So my understanding is that it is only the physics, either through the perspective of Einstein by just using equilibration, or our microscopic derivation using field quantization, which allows us to understand the phenomenon of spontaneous emission. Other questions? Okay, then before we talk about some really cute and nice aspects of the fully quantized Hamiltonian, I want to spend a few minutes talking about degeneracy factors. I've already given you my opinion. You should not think in almost all situations about levels which have a degeneracy. Just think about states. A state is a state and it counts as one. And if you have a level which has triple degeneracy, well, it has 3 states. Just kind of count the states and look at the states. However, there are formula for which involve degeneracy factors. And just to remind you, when we had the discussion of Einstein's A and B coefficient, the Einstein A coefficient was proportional to the B coefficient connecting responsible for stimulated emission from the excited to the ground state. But the Einstein B coefficient for absorption was related to the Einstein B coefficient for stimulated emission by involving these degeneracy factors. So degeneracies appear, and in some formulae, it makes a lot of sense to use them. So also I've always said for fundamental understanding, you should just assume all degeneracies are 1. This is how you can avoid sort of some baggage in deriving equations. And I'm still standing to my statement. I want to show you now a situation where it becomes useful to consider degeneracy factors. So let me give you an example. We can now look at the situation where we have an excited P state and a ground state which is S. Or I can look at the opposite situation where we have an S state which can radiate to a P state. Well, by symmetry, the different P states, m+1, m-1, m equals 0, are just connected by spatial rotations. So therefore, the lifetime of the P state, of the 3 P states, and the rate of spontaneous emission are the same. But if you now assume that you have absorption, you go from the S state to the P state, then you find that the Einstein B coefficient for absorption, there are now 3 possible ways, not just one polarization, all 3 polarization, and you will find that this is proportional to 3 times R. However, in this situation, it's a reverse, but let me just finish here. So here the natural line width and the rate of stimulated emission described by the B coefficient from the excited state to the ground state is proportional to R. Whereas in the other situation, if we have absorption now, well, each of those levels, there's only one transition, one pathway. Therefore, you will find that the coefficient for absorption is proportional to R, whereas gamma and the stimulated emission, which is now BSP, is proportional to 3R because there are 3 pathways. So depending what the situation is, you have to be careful. And you would say, but if it's an S to P transition, it may be connected by the same matrix element. And therefore, you would say, shouldn't there be a line strength which is independent whether you go from S to P or P to S, which just describes in a natural way what is really the coupling between S and P state? And yes, indeed, there is in the literature some definition of line strength where the line strength S would be proportional to the sum of all rates between an initial and a final state, and you sum over all. So therefore, when you use this formula for the line strings, whether you have the situation on the left side or on the right side, you would do always the sum over the three possible transitions, and so the line strength is the same for both situations. It's just generic for an S to P transition. So if you use this definition, but then you have the situation that spontaneous emission is always given by the line strength, but you have to multiply now by the multiplicity of the excited state. If you have a P state, the whole line strength is distributed over 3 states, and each state has only a spontaneous emission rate which is a third of what the line strength gives you. I don't want to beat it to death because I hate degeneracy factors, but I just thought this example with the P to S and S to P transition tells you why they necessarily have to appear in derivations like Einstein's A and B coefficient. I hope there are no further questions about degeneracies. Well, but it also, making this comment also allows me to say, well, when we derived when I derived the Einstein A coefficient, what we did last class, I did not use any degeneracy factors. Well, this is correct. Our derivation assumed that we assumed that there is only one final state. We did not include degeneracy factors. We also assumed that we had a dipole matrix element which was along the z-axis. And so by those definitions, I have implicitly picked a geometry which can be represented by that we have an excited P state in the m equals 0 state, and we have a pi transition with linear polarization to the S state. And by doing that, I did not have to account for any degeneracies. But in general, if you derive microscopically an equation for spontaneous emission, you may have to take into account that your excited state has different transitions, sigma plus and sigma minus transitions to different states, and you have to be careful how you do the sum over all possible final states. And this is where degeneracies would eventually matter. Questions? Okay, so then let's go from P counting or accounting for the number of states to something which is hopefully more exciting. We want to talk about the fully quantized Hamiltonian. So what we are working towards now, and it may spill over into the Wednesday class, is I want to give you the sort of paradigmatic example of cavity QED, where an atom within an excited state is in an empty cavity. And now it can emit a photon into the mode of the cavity. but this photon can be reabsorbed. So this is the phenomenon of vacuum-Rabi oscillations. And so I want to set up the Hamiltonian and then the equation to demonstrate to you the vacuum-Rabi oscillations. And for me, the vacuum-Rabi oscillations are the demonstration that spontaneous emission has no randomness, no spontaneity, so to speak, because you can observe coherent oscillation, a coherent time evolution of the whole system, and which is possible only due to spontaneous emission. So let's go there. So a few lectures just to make the connection. A few lectures ago, we had a semi-classical Hamiltonian, where this is when I wanted to show you that a two-level electronic system can be mapped onto a spin 1/2 system driven by magnetic field. So this was when we only looked at the stimulated term, when we only did perturbation theory. And in that situation, we had the electronic excitation, and then we had the drive field, which was assumed to be purely classical, like a rotating magnetic field which drives spin-up, spin-down transitions magnetically. And we concluded that, yes, if we use a laser field, it does exactly the same to a two-level atom what a magnetic field does to spin-up, spin-down. But now we are one step further. We've quantized the electromagnetic field and we have spontaneous emission, and this is something, for reason I've just mentioned, you will never find in spin-up, spin-down because it will take 1,000 years for spontaneous emission to happen. So now we want to actually go beyond this semi-classical picture, which is fully analogous to the precession and rotation of a spin in a magnetic field, and we want to add spontaneous emission. So what we had here is the Rabi frequency was the matrix element, the dipole matrix element, times a classical electric field. And we want to replace that now by the electric field at the position of the atom, but we want to use the fully quantized version of the electric field. And it also becomes useful to look at the sigma x operator, which is actually has two matrix elements off diagonal, which connects ground excited and excited ground state. And one of them is, it's going from the excited to the ground state. So this is sort of lowering the energy. It's a sigma minus operator. And the other one will be a raising operator. It raises the excitation of the atom, and we will refer to it as sigma plus. So the electric field is replaced by the operator obtained from the fully quantized picture. Here we have the prefactor, which is the electric field of a single photon or half a photon, whatever, but it's factors of 2 or square root 2. We have the polarization. And now, if you would take the previous result and would look at it, well, we want to go to the Schrödinger picture, and I mentioned that in the Schrödinger picture, the operators are time independent, so we cancel the e to the I omega t term. If you would go to the result we had last week and would simply get rid of the e to the I omega t term, you would now find operators A and A dagger, but they would have factors of I in front of it. That's the equation we had when we derived it. Well, I prefer now to use something which is looks nicer, just use A and A dagger, and you can obtain that by shift the origin of time. So we are not looking e to the I omega t at t equals 0. We wait a quarter period until e to the I omega t just gives us factors of I which conveniently cancel the other factors of I. But so what I'm doing is just for convenience. And let me write down that this is in the Schrödinger picture. Okay, so we want to absorb all constant by in one constant now, which is the single photon Rabi frequency. We have the dipole matrix element of the atom. There's a dot product with the polarization of the light. And then we have the electric field amplitude of a single photon, h bar omega over 2 epsilon naught v. So this is what appears in the coupling. And we want to write it as h bar omega 1 over 2. And this omega 1 is the single photon Rabi frequency. And with that, we have now a Hamiltonian, which is really a classic Hamiltonian written down in the standard form. It has the excitation energy times the sigma z matrix. It has the single photon Rabi frequency. The single photon Rabi frequency appears, this is the single photon Rabi frequency, but then the operator for the electric field after getting rid of the ice is simply h plus h dagger. H plus h dagger. And so this takes care of the photon field, and the operator which acts on the atoms are the raising and lowering operator sigma plus and sigma minus. And finally, we have the Hamiltonian which describes the photon field, which is h bar omega times E dagger E, the photon number operator. Any questions? Yes?
So what happened to the plane wave expansion? So we got rid of the e to the I omega terms, and why did we not have
I mean, we are looking at the interaction with an atom which is at rest at the origin, therefore e to the ikr is 0. We will only consider the spatial dependence e to the ikr when we allow the atom to move. As long as the atom is stationary, for convenience, we put the atom at r equals 0. But in 8422, when we talk about light forces and laser cooling, then it becomes essential to allow the photon to move, and this is actually where the recoil and the light forces come into play. But as long as we're not interested in light forces, only in the internal dynamics, ground and excited state, we can conveniently neglect all spatial dependencies. Other questions? So this is really a famous Hamiltonian, and you also see how natural the definition are of the single photon Rabi frequency. So we have 1/2 h bar omega with the diagonal sigma z matrix. This is the atomic excitation. This is the unperturbed Hamiltonian of the atom. This is the unperturbed Hamiltonian of the photon. And now the two are coupled. And the coupling is a product of an operator acting on the photon field, plus minus 1 photon. And the other one is an operator acting on the atoms, and it is plus minus an atomic excitation. So let me just remind you of that. The sigma plus and sigma minus operator. The sigma plus is the atomic raising operator, which takes the ground to the excited state. And the sigma minus operator is the atomic lowering operator, which takes the atom from the excited to the ground state. So this is our Hamiltonian. And the Hilbert space on which this Hamiltonian acts is the product space of the atom, direct product with the states of the light. Or in other words, a basis state would be that we use for the atoms the states which have 0 or 1 quantum of excitation. So we use excited state or ground state. And for the photon, we can just use the Fock states with where the occupation number is n. Questions about that? So it's a very, just look at it with some enjoyment for a few seconds. I mean, this is a Hamiltonian which has just a few terms. But what is behind it is, of course, the power of all the definitions. I mean, each symbol has so much meaning. But in the end, by having this formalism of operators, quantized electromagnetic field, we can write down, we can catch many, many aspects of, or we can pretty much fully describe how a two-level system interacts with a quantized electromagnetic field with that set of equations. Of course, the fact is not that everything is so simple. The fact is that we have, by understanding the physics, we have skillfully made definitions which allow us to write it down, to write everything down in this compact form. So often something is simple to write down, but if there's a lot of physics inside, we spend some time in discussing it. And the first thing I want to just point out and discuss is this interaction term. We have the product of sigma plus and sigma minus with A and A dagger. So what we have here is we have an interaction term. And this interaction part has actually 4 terms. In a very natural way. Well, let me just write them down. It's sigma plus with A, sigma minus with A dagger, sigma plus with A dagger, and sigma minus with A. Okay, so let's discuss those. Sigma plus with A dagger, sigma plus is actually, this is an absorption process. A reduces the photon number by 1 and increases the atomic excitation from the ground to the excited state. The other term looks naturally and intuitively like emission. The A dagger operator takes us from n to n plus 1, and sigma minus takes us from the excited state to the ground state. So these are the 2 terms which we would call intuitive terms because they make sense. The other terms are somewhat more tricky. Sigma plus and A dagger means we create a photon and we create an excitation. So in other words, it's not that like the other term, 1 quantum of excitation disappears from the field, appears in the atom and vice versa. Sigma plus A dagger means we have an atom excitation takes us from the ground to the excited state, plus we emit a photon at the same time. And sigma minus a dagger means that we go from the excited to the ground state. So we have an atom de-excitation. And now you would say, well, if the atom is de-excited, it should emit a photon. But instead, a photon disappears. So we have those processes. The last two are sometimes referred to in the theoretical literature. They are off-shell. On the shell is energy conservation. Off-shell means they cannot conserve energy, but nevertheless, these are terms which appear in the operator. But you should be used to, if you have often terms in the operator which cannot drive a resonant transition. When we looked at the DC Stark effect, or when we looked at the AC Stark effect for low frequency photons, those low frequency photons cannot excite an atom to the excited state, but nevertheless, so they are not causing a transition, but they led to energy shifts in second order perturbation theory. So therefore, those terms, that's language now, cannot drive transitions. They can only drive transitions to virtual states, which would mean they can only appear in second order perturbation theory, that you go up to a so-called virtual state, but you immediately go down. And those terms give only rise to shifts. No transitions, because you couldn't conserve energy in a transition, but you can do shifts in second order. And one example, which we discussed in the clicker question, is that those shifts are actually lamp shifts, and in other places, especially in the context of microwave fields, they are called Bloch-Siegert shifts. And let's just look at one specific state. And this is the simplest of all. We have the vacuum, no photons, and the atom is in the ground state. If you look at the four possibilities of the interaction term, there is only one non-vanishing term. The photon is at the bottom of all possible states. The atom is at all bottom of the possible states. So when we act with the four terms on it, the only term which contributes is where both are raised, because all the others are zero. The only non-vanishing term is where we create a virtual atomic excitation and also a virtual excitation of the photon field. And we know that when we have an atom in the ground state in the vacuum, that the only manifestation of the electromagnetic field is, of course, not spontaneous emission, but the lamp shift. So therefore, if you would apply this operator to the bound state of an electron in an atom, use the complicated 1s wave function of hydrogen, and sum this operator over all modes of the electromagnetic field, then you would have done a first principle QED calculation of the lamp shift. I'm not doing it, but you should understand that this operator, sigma plus a dagger, this is your operator for the lamp shift. Questions? Yes?
What effects does this Hamiltonian ignore? So does it, for example, capture radiation reaction?
Oh no, everything is, if you have a two-level system, this Hamiltonian captures everything which appears in nature if you have a two-level system interacting with the electromagnetic field. That's it. A radiation reaction is just something we can pull out of here. Stimulated emission we can pull out of here. The way how vacuum fluctuations create a lamp shift, or the way how vacuum fluctuations affect an atom in the excited state, everything is included in here. The question is just, can we solve it? And the calculations can get involved. But this is the full QED Hamiltonian for two-level system. That's the full picture. I mean, that's why I sort of said before, be proud of it. You understand the full picture how two-level systems interact with electromagnetic radiation. The only complication is, yes, if you put more levels into it and such, and things can get richer and richer. And yes, we have also made the dipole approximation, which I'm just wondering how critical it is. Well, we use the electric field A and A dagger, but my gut feeling is it doesn't really matter. What we have here is the most generic term which can create and annihilate photons, and we have the A and A dagger term. Actually, I don't know what would happen if you don't make the dipole approximation. Well, if you have two levels which are coupled by magnetic dipole, then you have the same situation. It is just your prefactor, the single photon Rabi frequency, is now alpha times smaller because of the smaller dipole matrix element. So you can, I think you can pick pretty much any level you want, and this is why I actually discussed matrix elements at the beginning of the unit. For pretty much all of the discussion we want to have, it doesn't really matter what kind of transition you have, as long as the transition creates or annihilates a photon, and all the physics of the multiplicity of the transition, magnetic, dipole, electric, quadrupolar, whatever, just defines what the single photon Rabi frequency is. The only thing, you've put me on the spot, but the only thing which comes to my mind now is if we would formulate QED not in the dipole approximation, but with the P minus A formulation, then we have an A square term, and then we have the possibility that one transition can emit two photons. So that's not included here. This would be something higher order. On the other hand, we can show with the canonical transformation that the P minus A formulation with the A square term is equivalent to dipole approximation. So the question whether you have a transition which emits two photons simultaneously or two photons sequentially by going through an intermediate state, this is not a fundamental distinction. You can have one description of your quantum system where two photons are emitted in one transition. You have another description of your quantum system where photons cannot, only one photon can be emitted, and then you have to land in intermediate state. And you would say, well, either two photons at once or one photon at a time. This is two different kinds of physics, but we can show that the two pictures are connected with a canonical transformation. So therefore, you have two descriptions here. But anyway, I'm going a little bit beyond my knowledge. I'm just telling you bits and pieces I know. But this Hamiltonian is either generally exact, I just don't know how to prove it, but it really captures in all of the QED aspects of the system we want to get into. So, okay. So, in many situations, we may decide that the off-shell terms of the interaction just create level shifts, lamp shifts, Bloch-Siegert shifts, And we may simply absorb those lamp shifts in our atomic energy levels, omega E and omega G. So therefore, for the dynamic of the system, if we include all those lamp shifts in the atomic description, we do not need those off-shell counterintuitive terms. These are actually also the counter-rotating terms in the semi-classical approximation. We only keep the intuitive terms, and that's called, again, the rotating wave approximation. Just to remind you, we do not have rotating waves here. Everything is operators, but the same kind of physics, co- and counter-rotating, appears here, that we have 4 terms. Two are the fully quantized version of the co-rotating terms, and the other 2, the off-shell terms, are the quantized version of the counter-rotating term. So therefore, if we neglect those 2 off-shell terms, we have now the fully quantized Hamiltonian in the rotating wave approximation. So let me just write it down because it's also a beautiful line. We have the electronic system. We have the interaction Hamiltonian, which has now only 2 terms. When we raise the atomic excitation, we lower the photon excitation, and vice versa. And we have the Hamiltonian for the photon field, E dagger A. And this is, apart from those lamp shift terms, the full QED description of the system. And if we only consider one mode, here, of course, in general, the general Hamiltonian has to be summed over all modes, and then we would get spontaneous emission and everything we want. But if you have a situation where you only look at one single mode, then you have what is called the famous Jaynes-Cummings model. And a very important result of this Jaynes-Cummings model are the vacuum Rabi oscillations, which I want to discuss now. Okay. So let me just, it's called Jaynes-Cummings model. So let me describe to you why it is a model. Well, it assumes a 2-level system, which we find a lot of candidates among the atoms we want. Sure, our atoms have hyperfine states, but we can always select a situation where essentially we only couple 2 states. We can prepare initial state by optical pumping and then use circularly polarized light on a cycling transition. And this is how we prepare in the laboratory a 2-level system. So that's one assumption of this model with a 2-level system. But the second assumption is that the atom only interacts with a single mode. And that requires a little bit engineering because it means we need a cavity. So let me just set up the system. So our laboratory is a big box of volume V. And this is where we maybe quantize the electromagnetic field to calculate spontaneous emission. And our atom here may actually decay with the rate gamma, which is given by the Einstein A coefficient. And in order to describe this spontaneous emission, we quantize the electromagnetic field in the large volume V. But now we have a cavity with 2 mirrors. The And those two mirrors define one mode of the electromagnetic field, which will be in resonance or near resonance with the atom. Well, there will be some losses out of the cavity, which eventually couple the electromagnetic mode inside the cavity to the other modes in this bigger volume V, and this is described by a cavity damping constant kappa. What is also important is when we use cavity to single out one mode of the electromagnetic field, the cavity volume is V prime, and we often make it very small by putting the atoms in a cavity where the mirror spacing is extremely small. Okay, we know, and I'm not writing it down again, what the Einstein A coefficient is. The Rabi frequency, the single photon Rabi frequency, which couples the atom to the one mode of the cavity, has this important prefactor, which was or is the electric field of one photon in the cavity. And importantly, it involves the electric field of the photon in the cavity volume, which is V prime. So now, in addition to using, now you see what our experimental handle is. If we make this volume very small, then we can enter this strong coupling regime, where the single photon Rabi frequency for this one mode selected by the cavity becomes much larger than the spontaneous emission into all the many other modes. So the interaction with one mode due to the cavity and the smallness of the volume is sort of outperforming all these many, many modes of the surroundings. And that would mean that an atom in an excited state is more likely to emit into the mode between the two cavity mirrors than to any other modes to the side. Secondly, of course, when the photon has been emitted into the cavity, the photon can still couple to the other modes by cavity losses kappa. And now we assume that we have such high reflectivity mirrors that kappa is smaller than the single photon Rabi frequency. And this is called the strong coupling regime of cavity QED. So then we can at least observe for limited time the interplay between a single mode of the cavity and a two-level system, and this is the James-Cummings model, the James-Cummings model. So in that situation, the Hamiltonian, the fully quantized Hamiltonian, the QED Hamiltonian, couples only pairs of states, which are, we label those states the manifold n. So we have an excited state with n photons, and it is coupled to the ground state with one more photon. Our Hamiltonian has two coupling terms. You remember the other two were neglected in the rotating wave approximation, and we can go from left to right with sigma minus A dagger plus, and we can go from right to left with the operator sigma plus and the annihilation operator A. So as long as we have a detuning delta, which is relatively small, we do not as long as we detune, which is relatively small, the rotating wave approximation is excellent. So let me just conclude by writing down the Hamiltonian for the situation I just discussed, and then we discuss the Hamiltonian on Wednesday. So if this is energy, we have two levels. The excited state with n photons, the ground state with n plus 1 photons. If the photons are on resonance, the two levels are degenerate. But if we have a detuning delta, the two levels are split by delta. And what we are doing right now is, when we write down the Hamiltonian, we shift the origin. So the zero of the energy is just halfway between those two states. That's natural. So this avoids just offsets in our equations. And so our Hamiltonian has now the splitting of plus minus delta over 2. The coupling has the prefactor, which is the single photon Rabi frequency. And then the A and A dagger terms depend on n square root n plus 1. So what I wrote down now is the Hamiltonian rotating wave approximation, which describes only one pair of states, but we have sort of course, in our Hilbert space, one pair of states for each label n, but each of them is sort of described by a decoupled Hamiltonian. So that's what I wanted to present you today. And I will show you on Wednesday how this Hamiltonian leads to Rabi oscillations, not induced by an external field, but induced by the vacuum. Any questions?